Now that we've looked at decimals a little bit, let's look at them a little bit further by examining operations on decimals and repeating decimals. So we'll start with the operations on decimals and think about what we know about addition and subtraction of decimals. Now we know that when we add and subtract decimals that we're supposed to line up the decimal points, but why do we have to do that? Well, I'd like you to think about these two numbers that we're trying to add, 2 and 13/100ths plus 4 and 5/10ths. Now actually saying those numbers that way is a bit of a hint about why we're adding up or lining up the decimal points. Because when we have a decimal number, it is composed of a whole number part plus a fraction part. So if we think about the expanded form of these numbers, we know that 2 and 13/100ths is 2 plus a tenth plus 3/100ths. And 4 and 5/10ths is the whole number 4 plus 5/10ths. Now we know that when we add fractions, we can only add fractions with like denominators. And how do we add these fractions with like denominators? How do we make sure that we are adding those like denominated fractions together? Well, we do that by lining up the decimal points, because lining up the decimal points assures that we will be lining up our whole number values and our fractional values that have denominators of 10 and our fractional values that have denominators of 100. So let's take a look at a subtraction problem. With subtraction, we have the same issue as addition. We have to make sure that we are going to be subtracting the fractional portions that have the same denominator. And we do that by lining up the place values. Now when we subtract, we have to think about taking away. And if you look at the 1 that's in the hundredths place of the 3 and 51/100ths, we're trying to take that 1/100th away from, well, there's nothing in the hundredths place in the 12 and 8/10ths. So that's the real reason why we put these placeholder zeros in after the decimal point in the numbers. Saying 12 and 80/100ths is exactly the same as saying 12 and 8/10ths. But by saying 12 and 80/100ths, we now can look at how we do the subtraction of 1/100th taken away from 0/100ths. Now just like with whole number subtraction, we may need to do some regrouping. So we can take one of these tenths away from the 8/10ths and regroup it as 10/100ths so that we can do the subtraction. 10/100ths minus 1/100th is 9/100ths. 7/10ths minus 5/10ths is 2/10ths. And 12 minus 3 is 9. So we have our difference 9 and 29/100ths. Now when we're multiplying decimals, we can also think about the place value considerations of those fractional parts of the number. So if we think about 3 and 2/10ths times 4 and 7/10ths, what we're really doing is multiplying two numbers together that represent mixed numbers. We know that when we multiply mixed numbers together, we have to be a little bit careful, because we either need to think of that as a problem in which we're multiplying a binomial times a binomial, or we can rewrite the mixed numbers as improper fractions and multiply. And if we do that, we know that we multiply the numerators together and then we multiply denominators together. So we have 1,504/100ths, which is 15 and 4/100ths when we do some regrouping. Now, is that how we multiply decimal numbers together generally? Well, no, we have an algorithm for doing that, and the algorithm goes something like this. Ignore the decimal points and simply multiply the numbers as if they're whole numbers. So if we do that, we get this number 1,504. Now that should look pretty familiar. That's the same as the number we got in the numerator when we multiplied the two mixed numbers together after changing them to improper fractions. So where does the 15 4/100ths come from? Well, if we look at the number of digits we have after the decimal point, what we're really looking at is how many times a factor of 10 is being used in a denominator of a fraction. So the 3 2/10 means we have one factor of 10. There's one digit behind the decimal point. One factor of 10 in the denominator of an improper fraction that represents 3 2/10. And the 4 7/100ths has one digit behind the decimal point. That's where that 10 in the denominator of 47/10 is coming from, which means with the two digits after the decimal point that we have two factors of 10 in our denominator, which is 100. That's why when we put the decimal point in our final answer, we move that decimal point 2 places to the left, because we're saying, hey, we're going to be dividing by two factors of 10. That means we're dividing by two tens times themselves, 10 times 10. We're dividing by 100, which moves the decimal point over 2 places to the left. Now you may remember that when we multiplied whole numbers together, we had something called the lattice method. And we can actually use the lattice method to multiply decimal numbers as well. So let's multiply these same two numbers with the lattice method. We know that 3 times 4 is 12, 2 times 4 is 8, 3 times 7 is 21, and 2 times 7 is 14. And if we add along the diagonals, we're adding digits that are in the same place values. So 4 is the only digit in our first place. 8 plus 1 plus 1 is 10. 1 plus 0 plus 2 plus 2 is 5. And then 1 is the only digit in our last place. So how do we get that decimal point in our answer if we're using this lattice method? Well, remember, the lattice method is simply a way to organize place value, and even those decimal points get organized in this process. If you follow those decimal points down and to the left and see where they meet and follow that diagonal out, you'll get the position of the decimal point in the product. So there's our 15 4/100ths. So let's look at division of decimals, and we're going to start with a fairly simple decimal division problem. We've got 6/10 divided by 2/10. And let's think about what that really is saying we want to do. It's saying we want to divide 6/10 into groups that each contain 2/10. Now think about some of the models we've looked at already with decimals. If I consider that square to be a whole and then divide it up into 10 equal pieces, each of those 10 pieces is a tenth. So I'm starting with 6/10 and I want to divide it into groups that each contain 2/10. How many groups do I end up with? Well, there's one group with 2/10 in it, two groups with 2/10, and three groups with 2/10. So since I end up with three groups each containing 2/10, I know that 6/10 divided by 2/10 is 3. Now you know that when we do decimal division, there's something we do with moving decimal points around. So let's think about why we're going to be doing that when we divide. If we have 6/10 divided by 2/10, that's the same thing as this fraction, 6/10 over 2/10. A fraction is a division problem. And I can multiply the numerator and denominator of a fraction by the same number and have an equivalent fraction. So if I do that, if I multiply the numerator and denominator of this fraction by 10, I end up with 6 divided by 2, which is an equivalent fraction, an equivalent division problem to what I started with. Obviously, 6 divided by 2 is 3. So I can get the same result, I can get the same quotient if I multiply the numerator and denominator of the fraction by the same power of 10. So how do we deal with that when we're doing a division problem? Let's say we want to take 15 and 12/100ths and divide it by 2 and 7/10ths. So we're saying divide 15 and 12/100ths into groups that each contain 2 and 7/10ths. How many groups will we have? Now let's think about what has to happen with these decimal points to make this an easier division problem to do. It's hard to imagine what a group that contains 2 and 7/10ths is going to look like. But if I multiply numerator and denominator of this fraction by 10, I've got an equivalent fraction that says take 151 and 2/10ths and divide it into groups that each contain 27. Now that's an easier thing to imagine, dividing into groups that each contain 27. That's why when we do a division with decimals, we always take that decimal point that we see in the divisor and we move it all the way over to the right. That means we're multiplying that divisor by 10. But if we're going to multiply the divisor by 10, we have to also multiply the dividend by 10, which is why we're actually moving those decimal points over the same number of places on both of these numbers. So now we're trying to decide how many times 27 goes into 151.2. And when we do our division, we find out that we have a quotient of 5.6. So if we were to divide 151.2, 151 and 2/10ths into groups that each contain 27, we would have 5 and 6/10ths groups. Remember, that's exactly the same quotient as taking 15 and 12/100ths and dividing it by 2 and 7/10ths. Now when we do a division, we know that we get a decimal number, and in the last problem we saw a decimal that terminated, that 5 and 6/10ths. Decimals don't always terminate, sometimes they repeat. A repeating decimal can be represented as a fraction, and we've already seen that if a fraction can be written as a terminating decimal, then its denominator will only have factors of 2 and or 5. If we have a repeating decimal, then we know that the fraction that we write this decimal as will have some factors in the denominator that are not 2's or 5's. So let's think about what repeating decimals look like when we write them. There's two ways to write a repeating decimal. One way is with this bar notation. The bar over the digit or digits of a repeating decimal indicate which digits repeat over and over and over again. So in this case, the 3 is going to repeat over and over infinitely. So we could actually write this decimal in that form. The 0 does not repeat because it does not have the bar over it, but the 3 does repeat forever. Now think about which digits repeat on this decimal. The bar is only over the 6 and the 5. It's not over the 3 and the 4. So the 3 and 4 don't repeat, but then after that the 6, 5, 6, 5, 6, 5, 6, 5 goes on forever and ever and ever. So we could write that decimal in this form as well. So if we have a fraction, we want to write it as a decimal. We've already looked at a couple of ways to do that. If we know that we're going to have a repeating decimal, and I certainly see that we will in this case because the 22 that's in the denominator has a factor of 11 in it, and that's not a 2 or a 5. If we know that we're going to have a repeating decimal, then we're going to do a division to change that fraction into a decimal. Now I know this is going to repeat, and I need to continue the division until I'm certain that I have determined what the digits are that repeat. So there are no groups of 22 and 5, but if I look at that 5 as 50/10ths, there are 2/10ths inside that 50/10ths. 2 times 22 is 44. Let's subtract. Let's see, 22 goes into 62 times. Oh, now look at that. The 2's seem to be repeating. So should we stop at this point? Well, not yet. Keep going with your division, because what we want to see is that we're certain that we found the repeat. And if I keep doing the division, I find, oh, nope, that doesn't, the 2's don't continue, do they? Now I've got a 7. Now that's interesting. Do you see the 60 that we just got when we subtracted? We got that same 60 when we subtracted before. So that means we're on to something. We're going to see that repeat happening. 22 goes into 60 twice. 22 goes into 167 times. All right, so we definitely have something repeating here. But can you tell what's repeating? It's a little tricky. Obviously the first 0 isn't repeating. The big question is that first 2 after the decimal point, that first 2 in the tenths place, is that repeating? And the answer is no, that one doesn't repeat, but the 2 and the 7 after that do repeat. So to write this using the notation with a bar, we would write 0.2 and then the 2, 7 repeats. Now we've talked about ordering decimal numbers from smallest to largest when they terminated. What if we throw some repeating decimals in there and we want to order these from smallest to largest? Now when we did this before, we compared the numbers digit by digit according to their place values, and we're going to do the same thing here. But these numbers are written in different forms. 3.6 is a terminating decimal. This 3.6, where the 6 repeats, is not a terminating decimal. It repeats. And this one repeats as well, and so does this one. So how are we going to compare these numbers? Well, we're going to expand them. So the first repeating decimal has a repeating 6. This one has a repeating 6 as well after the 7. And this one has a repeating 6.3. Now if we think about the 3 6/10 as also kind of being a repeating decimal, it really isn't, but we could write as many zeros in there as we want. Now we can compare digit by digit with these decimals. They all have 3 wholes. We're looking for the smallest number, so if we look at the tenths, well, it's pretty clear that the first, the second, and the last number all have 6/10. So one of those has got to be the smallest. So go to the 100th digit with those 3 numbers, and you'll see that the first number has a 0 in the hundredths place, which is smaller than the numbers in the hundredths places for the second and the fourth number. So that number has to be smallest. Now we're going to figure out what's the next smallest. So once again, looking at the 3 numbers we have left, we know they're all the same in the whole number place. In the tenths place, it's either that first one or the third one that we have left, because they both have 6/10, which is smaller than the 7/10 in the other number. If you go to the hundredths place, you'll see that the very last number has only 3/100ths, as opposed to the 6/100ths that the first of those numbers has. So the last number has to be second. And now comparing the remaining numbers, they both have 3 wholes, but the first number that's left has only 6/10, while the other number has 7/10, so it has to be the smaller of the 2 numbers, which means when we write the numbers as they originally were given to us in order, we have 3 6/10, then 3 and then the 63/100ths is repeating, so 3.63 repeating, and then 3.6 repeating, and then 3.76 repeating. So if we can write a fraction as a repeating decimal, how do we take a repeating decimal and write it as a fraction? Well, we're going to rely on something that we learned in algebra to do that. So let's think of this number that we are trying to write as a fraction in its more expanded form. So we'll think of that as 0.1212121212. That goes on forever and ever. And we'll call that x. So that's our number. That's the one we're trying to change into a fraction. And if we can figure out what fraction that is, if we can figure out what x is, then we'll have our fraction. Now the problem with that is it's got all these digits that just continue on forever and ever and ever. And what we'd like to do is write a fraction that doesn't have all these repeating digits in it. So we need to find a way to get rid of those repeating digits. Now what's important to notice is there's 2 repeating digits in this number. So if we multiply both sides of that equation by 100, then we would have 100x equals, and then think about what happens with the decimal. Multiplying that decimal number times 100 moves the decimal point over 2 places. And so we get 100x is 12.1212121212. Now here's why that's going to be helpful. What we're going to do is subtract the second equation from the first. So on the left side, 100x minus x is 99x. And on the right side, all those repeating digits, they line up. So when we subtract, they'll subtract off. And all we'll have left on the right side is 12, because 12 minus 0 is 12. And remember, we're trying to figure out what x is, because that was our original number. So if we divide both sides by 99 and simplify, we get that x equals 4/33. So the repeating decimal we started with can be written as 4/33 as a fraction. Let's try that one more time. Now we've got a decimal number 3.6 repeating. The 6 is repeating over and over and over and over and over again. So what we're going to do is start by saying, okay, I don't know what fraction that is, but I'm just going to call it x. And I'm going to expand the 6. So now I'm going to look to see how many digits repeat. And there's only one digit that repeats. That's the 6, over and over and over again. So I'll multiply both sides of the equation by just 10 in this case. That's 1 power of 10. Because by doing that, the repeating digits are going to line up with each other, so that when I subtract, all those repeating digits are going to subtract off. And I'll end up with 9x equals 33. And then divide both sides by 9 and simplify, and we get x equals 11/3. So 3 and with the 0.6 repeating is the same thing as the fraction 11/3. So you can see decimals have an awful lot to do with fractions, and all of those rules that we learned for doing fraction operations are really at play when we're working with decimals.